So today we are going to talk about this problem of the product of four consecutive numbers is always 1 less than a perfect square. I'm Shubhanshu, and in this video I'm going to talk about how we can solve this problem. So the problem can be more mathematically stated as follows. We select n, an integer, and then we have four consecutive numbers which are also integers defined by n plus 1, n plus 2 and n plus 3. Now the problem as stated basically asks that there always exists a k which is also an integer such that the following equation holds. That is, the left hand side is n plus 1, n plus 2 and n plus 3 is equal to k square minus 1. This is effectively a reframing of the statement that the product of four consecutive numbers is always equal to 1 less than a perfect square. So k square is the perfect square because k is an integer, and 1 less than the perfect square should be equal to the product. So let's see how we can prove this. So first let's actually look at some examples. So here we see a table of a set of four consecutive numbers and what is their product. So we have in the first row we have 1, 2, 3, 4, the first four consecutive natural numbers and their product 24, and we can now think of like we want k square minus 1 to be equal to 24. So let's look at the rightmost column, which is 24, and we can move backward that. So if k square minus 1 is 24, then k square is 25. We have just added 1, and then we can just take a square root, which is 5. So moving down, we see that the product and k square minus 1 match exactly in all the columns. So this gives us some intuition that yes, like looking at a few examples, this equation seems to be holding. But how can we prove this? Let's also look at the data. So on the leftmost plot we have the number n, which is the first number of the sequence of four consecutive numbers, and on the y-axis we have basically their product, and we see that like this is the product of the four consecutive numbers looks like as a function of n. Similarly, in the middle plot we have chosen like what the value k, which is the square root of y plus 1, that is like, you know, if we consider y is equal to k square minus 1, what that value look like for every k. And on the rightmost plot we have a plot for n, which is like, you know, again this original number, the first number, and how it maps to k, which is like, you know, what we want to get as the perfect square number k. So let's see. So the key idea of the proof comes from the right hand side of the equation. So if you observe the right hand side of the equation, it is k square minus 1. Now this can be rewritten as a product of two numbers, which is k minus 1 and k plus 1, and now this is where the hint lies. So if we rewrite our product k square minus 1 as k minus 1 into k plus 1, we start seeing like, you know, how that product can be formed. So the right hand side basically means that it is a product of two numbers which differ by 2. That is, those numbers are k minus 1 and k plus 1. So these numbers, if we like, you know, just find the difference, they differ by 2. So now if we can somehow show that the left hand side is also a product of two numbers which differ by 2, then the proof is done. And the key idea we are going to explore is how we can represent this product of four numbers as product of two numbers which differ by 2. And once we have found these two numbers whose product which differ by 2 and whose product equals to the product of the four numbers, then we can just map them to k minus 1 and k plus 1, and then we will find k. So let's start by grouping the numbers n plus 1, n plus 2, n plus 3 into pairs with the hope of getting something which maps to k minus 1 and k plus 1. So we are going to utilize a few facts in how we group these numbers. So the key idea there is, like, we can pair up these numbers and we can choose the pairs such that the product of these pairs only differs by a constant. So, and this constant, should be independent of n. And we're also going to utilize this fact that if we have, like, say, a product of two factors, say, let's say n plus I and n plus j, then this expands to n square plus I plus j into n plus I plus, into j. So basically the whole part which is independent of n is I into j, and the part which depends on n is like n square plus I plus j into n. So we can observe that, if I plus j will be the same for numbers which are equidistant from the middle of all numbers. So here, like, for example, we have n, n plus 1, n plus 2, n plus 3. So we can see that I plus j is same, like, for these two numbers. Like, we have n plus 1 and n plus 2. So I plus I, if we consider 1 is equal to I, 2 is equal to j. So we have 1 plus 2 is equal to 3. And same, we can write n is equal to n plus 0. So we have again like n and n plus 3. So I plus j is going to be 3 again. And now, using this intuition, we can select our pair of numbers. So the first pair which we choose is n and n plus 3, as described before. So what their product comes out to be n plus 3, which can be expanded to n square plus 3n. Now the second pair is n plus 1 and n plus 2. So again, their product is n plus 1 into n plus 2. So this can be expanded again to n square plus 3 and plus 2. So the thing which I've highlighted is the common part. And remember, we wanted the products to only differ by a constant which is independent of n. And we see this is happening. So the two products actually have the factor n square, have the part n square plus 3n common, and they only differ by the number 2. So effectively, now we have found those two numbers, but let's explore it a bit further. So we can, again get these calculations done, and we can verify that these two products differ by 2. So now we are ready to map these two numbers. So we found the first product was n squared plus 3n, and the second product was n squared plus 3n plus 2. So now the larger one can be mapped to k plus 1, and the smaller one can be mapped to k minus 1. And now we are almost done. So we are now going to use one of the equation, and we are going to find that k is equal to n squared plus 3n plus 1. And using this value of k, the following equation holds that, again, n squared plus 3n plus 2. So this is k plus 1 and n squared plus 3n. So effectively what we did, we added 1 and subtracted 1, so it's equal to k minus 1. So effectively now we have proved that for any 4 consecutive numbers, so that means for any value of n which is an integer, we get 4 consecutive numbers whose product can be mapped to a product to k square minus 1, where k is some integer. And this is how k comes out to be, and this is how those two numbers are formed. And this equation can be solved by choosing k is equal to n squared plus 3n plus 1. And yes, that closes the proof. Now let's verify it once again. So we found, as we saw in the previous example, initially we had these numbers and their products, and now we have found k. So remember, the k which we were hoping for from the back calculation is exactly the k which we found using the formula we have derived in our proof. So we have k is equal to 5, k is equal to 11, and so on. And again, we just use the red dotted line to map this k is equal to n squared plus 3n plus 1, and it exactly maps to the original original curve of k versus n. So that closes the proof, and I'll be making more videos, so stay tuned. Thank you.